Alright, so sorry about shutting down the video on the last video. I meant to hit the pause and I hit the stop button. Um, and I had already gone too far to redo it, so okay, let's see if we can get through this. We need an algorithm to find the global max and min, and this is going to be called the closed interval method. So just to give you a hint about what's going on here, let's draw a function uh, and see which points we have to maybe look at to see if we have a max or min. So from this graph, I think you see we have to check endpoints. Check endpoints for the function because that's where the derivative may not be zero, but we still might have a global max or min at an endpoint. We also have to check where the derivative is equal to zero, right? Maybe the derivative is zero here, and then it does not exist there. So check. Is there a name for those points? By the way, there's another point where the derivative does not exist. Critical points. And so the algorithm is basically just checking endpoints and critical points and finding the max or min. So let's write that down as an algorithm. So the closed interval method. And this is for finding a global max and min for a continuous function on a closed interval. Right, so actually my long title there actually tells us what our input and our output to the algorithm is. Our input, so I'm going to kind of write this like a computer algorithm. The input would be the continuous function, f. Maybe I'll write continuous in parentheses, continuous, and the interval, ab. What's your output? The output is the global max and global min. Now usually you don't just write down the y values. These are y values, right? The global max and global min. And write down where they occur. Okay, so this is also kind of important to know where in the interval the max and min occurs. Good. So let's try an example. I'm going to try to pause this and not hit the stop button. And then we'll try an example. Okay, so here's our function. It's a beautiful polynomial, and we know polynomials are nice, continuous, differentiable functions. So in this case, we don't have to worry about where the derivative does not exist. Right? And then we have a closed interval from -2 to 1. Good. And so now we'll proceed. First thing we need to do is find the critical points. The CPs. And the critical points here, if I take the derivative, 3x squared plus 2x minus 1 equals 0. Now, you could go to the quadratic formula, but hopefully this factors. Does this factor nicely? Since it's a book problem, it probably does. Right, 3x and x guaranteed. And then, let's see, to get a minus 1 over here, I'm going to need either plus plus, or not plus plus, but minus plus. Which direction? It looks like -1 and +1, huh? And then we can just do a quick double check. That'd be plus 3x minus x would give us a 2x. Good. And so therefore x equals 1/3 and x equals -1 are the two critical points. Good. Step 2 is just to build the table. X, Y. And list your endpoints. I like to put things in order so I can kind of see where things are going. So that'd be -2, -1, and then 1/3 and 1. So notice again, those are endpoints. So endpoint, endpoint, endpoint. And then these are critical points. Good. And then on this side, we'll just list the y values. So if I put in, let's see, scratch work. If I put in -2, I get -8 plus 4 minus 2. It looks like that's that's +2. -2. If I put in a minus 1, I get a minus 1, plus 1, minus plus 1. So that's going to be a plus 1. Good. If I plug in a 1/3, I get a 1/27th, plus a 1/9, minus a third. If I rewrite that quick as a bunny here, that's 1 plus 3 minus 9. Is that right? Minus 5/27. Good. And then if I put in a plus 1, I just get 1 plus 1 minus 1. Good. So minus 2, 1. That probably wasn't too entertaining to watch me do arithmetic. Okay. Very good. So let's point out the global max and min now. The global max is 1, right? And it occurs at 2 places. Occurs when x equals plus or minus 1. And then similarly, the global min is minus 2, and then occurs when x is equal to minus 2. Good. So now we have our maxes and our mins, and we're all done. I'll pause again, and then we'll try some more examples. Okay, so in this example, we'll just take a look at critical points. So find the critical points for g of theta equals 4 theta minus tangent theta. By the way, this is exercise number 40. All right. So we're not given an interval, so we have to assume all reals in this case. So we take a look. G prime of theta is going to be 4 minus secant squared theta. And because we're going to be solving this for theta, let's go ahead and write that as a cosine function. So that's going to be 4 minus 1 over cosine squared theta. Right? And so we're looking for where that's equal to 0 or where that does not exist. So we'll go ahead and continue that for the 0 case. And so that means that cosine squared theta is equal to 1/4, or cosine of theta is equal to plus or minus 1 over 2. Good. Now, where is cosine of theta equal to plus or minus 1 over 2? Is that one of our nice triangles? Let's take a look. So if this is theta, we have cosine theta is 1 over 2, so that's adjacent over hypotenuse, so the length of the third side is the square root of 3. Yay! Do you recognize that? Hopefully you do. Theta is equal to pi over 3. That's our 30, 60, 90 triangle. Good. And so for the other ones, you might go ahead and look at the unit circle. Because we're saying that cosine of theta can be plus or minus 1 over 2. The cosine is our x-coordinate. And so we found this angle, right? This angle was pi over 3. But you could be down here instead, and that would be what angle? Minus pi over 3. Or you could say 2 pi minus pi over 3. And if you do that, let's see, that's... Oops. That's 2 pi minus pi over 3, which is 6 pi minus pi, right? Over 3, which is 5 pi over 3. Good. So minus pi over 3 or 5 pi over 3. And then cosine could also be minus 1/2, so it could come over here instead. Right? So we would have this angle or this angle. This is going to be another pi over 3, so this is going to be pi, so 2 pi over 3, huh? And then what would this one be? This one would be pi plus pi over 3. So what's that? Pi plus pi over 3 is 4 pi over 3. So we see that theta is equal to pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, plus or minus 2 pi. Oh, maybe we should say, or multiples of 2 pi. We can add multiples of 2 pi. Okay, sorry about that. Good. Okay. Are those all my critical points? Let's see. Where is G? Does G prime of theta? G prime of theta does not exist. From the definition here, right? The cosine is in the denominator. So therefore we also have to watch where g prime of theta is equal to, let's see, where cosine of theta is equal to 0. Where is cosine of theta equal to 0? That's my cosine function. 2 pi, pi over 2 and 3 pi over 2, right? Pi over 2, 3 pi over 2. Good. All right. Now, here's a question. Those are points where g prime of 0 does not exist, but do we need to include them in our answer? Well, notice that pi over 2 and 3 pi over 2 are not included in the domain. These are not in the domain. Not in the domain of g. And so we typically would not include them. We would not include these. Although I should say it's always good to make a note that these are trouble points. It's just that because they're not in the domain of the original function, we wouldn't include them. Very good. Okay, let's try a couple more questions here. Question: true or false? If f prime of 2 equals 0, then f has a local max or min at x equals 2. So the question is, you could really say this is, if f prime of a equals 0, for example, then does f have a local max or min at x equals 2? So one way to think about that, if you have the derivative being 0, that just means that the function is locally a straight line. I don't know where. But does that necessarily mean you have a local max or min? What are some possibilities here? You could have a function that looks like this, in which case you would have a local min, or you could have a function that looks like that, where you have a local max, or you could have a function that looks like that, where you just have a plateau, right? And so in this case then we would say, no, this is false. Maybe neither local max or min. Good. On the other hand, maybe we'll try one more. True or false? If f has a local max at x equals a, then f prime of a equals 0. Is that true? In fact, it is true. If true, well, maybe I shouldn't say that then. I should say false. Because what could happen is you could have something like that. It is actually true if f prime of a, maybe I should say if f prime of a exists, then it is true. Oh, we're running way over time. We'll try some more examples in the next video.